Welcome for the announcement of this year's Nobel Prize. Has today decided to award the Nobel Prize in Physiology or Medicine jointly to...
Has this morning decided to award the Nobel Prize in Physics to... This has decided to award the Nobel Prize in Chemistry in equal shares to...
The Nobel Prize in Literature is awarded to...
Has decided to award the Nobel Peace Prize to
award Sveriges Riksbankspris in Economic Sciences in memory of Alfred Nobel to...
So the 2024 Nobel Prize in Physics will announce in the 8th October, 11:45 the CEST time. And in my case, this is the 5:30 p.m. in Seoul. So this is the evening. So just 1 hour remaining. So waiting for the announcements, I want to review the previous Nobel Physics Prize to check the current and recent research on the physics. So the many people await the announcements now, and they predict who is the winners of the Nobel Prize in Physics during this year. So yesterday the some medicines area the Nobel Prize analysis. And today's the Nobel Physics Prize analysis just 1 hour remaining. In the previous year, 2023, the after second person analysis, they received the Nobel Physics Prize. And because this is Harvard Physics Zoom in my YouTube channel, so I want to focus on Harvard physics, like as particle physics or quantum field theory, and also the cosmology of astrophysics. So this is the list for Nobel Physics Prize from the 91 to the 2023. Previous year, after second person analysis received the Nobel Physics Prize. Actually, it's the IMNAS expert in the optics and also for the solid state physical metaphysics. So I always keep about that. And 2 years ago, 2022, the experiments for the baryon nickel violations, they received the Nobel Prize. The baryon nickel is for the quantum some of the interpretations of the quantum observations. Also, the quantum entanglements are related with that. And 3 years ago, some of the all science areas are received the prize, like as a global warming modeling and the disorder in the complex system like the chaos. I want to focus on the 2020, the Rosa Parros, who is a mathematics, science, and also theoretical physicist in the UK. Rosa Parros is author of the laws of the reality. Actually, when I was the high school student, I read his book, The Law to Reality. At that time, I cannot understand because the law to reality, the book is very difficult, including some of the underground level and also graduate level. The first parts of the books that contains some mathematical physics, especially some mathematics of the complex number and some differential geometry and algebra. And the second part of his books discusses of the modern physics like quantum mechanics, the relative theory, in the point of view of the algebra and the geometry. And also he discussed several possible way to combine the quantum theories and the gravity theory. He suggests some twist theory and also compares between the string theory or quantum loop gravity. Actually, still I can understand his book, The Low to Reality, but the point is that books lead to me to have interested in the physics. And actually in the 2020, in October, that was a time of the COVID-19, and I was in my home, not in my campus or my lab. So I also watched the live streamings for the announcements of the World Physics Prize at the time, and I was very surprised uh, because Rosa Parlus is my one Rebel is the physicist for me. Actually, he is a mathematician. And he receives the Nobel Physics Prize due to the black hole predictions by the general relativity theory. He predicts the existence of the black hole mathematically. So at the times, I'm very happy to receive the news of the Rosa Parlus receives the Nobel Prize, and actually he is also the bronze of Stephen Hawking, who is famous by the black hole research. And actually, the Hawking died in the 2018 or 19 or at the time 70 years ago. And also in the 2020, the other topics is supermass compacts, like the galactic center. That discovers the lambda bounded by the such supermass fields. And in 2019, the James Peebles received the Nobel Prize by the standard cosmology, like the lambda CDM model. Actually, the cosmology is also important something in the hand of physics. Actually, we can investigate the new physics theory for the particle. They can be tested by the early universe cosmology because in the early universe, the scale factor is extremely small and the scale is very high, so we can reach the high energy scale. And then also the 2019, the explanet discovery received the Nobel Prize. 2018, actually at that time, I entered the undergraduate school, so I also watched the live streaming for the Nobel Physics Prize. And at that time, there's some areas of optics that receives the Nobel Prize, like the optical tweezer, the ultra-short optical pulse, but I am not exported it. 2017, the gravitational wave Gibson and other scientists received the Nobel Prize by the gravitational wave, so-called the GW. The GW is one solution of the Einstein field equations of the general relativity theory. Einstein field equations are actually the second linear differential equations with several components in the tensor to describe the manifold of the curved space-time. But we can perturbatively approximate the Einstein field equations with linear approximations. And the gravitational wave is one solution of that. And there are many efforts to detect the GW, almost third of bodies, and the LIGO detections collaborations success to discover and detect the gravitational wave with the interfered metals in 2016. Actually, they discovered the gravitational wave in 2015 and announced in 2016 February. And at that time, I bought several books in the general relativity theory because there was almost a 100 years anniversary for the general relativity theory, which is the constructs by the Einstein in the earliest times of 20th century. And also after the detection of the gravitational wave, it becomes a new method to detect the cosmological signal, like as a black hole collision or some of the early universe signal. Many particle physicists also participate in the gravitational wave, which is can be induced by the some early universe physics like cosmic string collision or phase transitions. I want to also study what gravitational waves say, but that's just a plan. So maybe if there's a chance of time, I will make the lectures seminars in the museum after I learned at the be familiar with the topic of the gravitational wave. And in 2016, the topological phase transitions are received. So at that time, maybe the Saulas receives the physics prize. He's a very older peoples at that time. They researched some 2D material, and the topological phase transitions like as the number of the hole, like the genus, which can classify the topological homology. There's some of the topics of the solid state physics, and I think that was a very hard to explain to the public and also for the scientists. But I'm not interested in the such a topological space transitions and solid state physics. And 2015, neutrino oscillations, which is my research topic. In the Japan, there are super Gamio-Kondes experiments, and in the Canada, SNL experiments. The leaders of those experiments received the Nobel Physics Prize. The neutrino physics is the first my research topics when I entered the graduate school. When I started in the individual studies in undergrad level, in the senior, the board grades of the undergrad level, I received the topic of the neutrino oscillation in the model, which is called MSW bubble model part. So neutrino oscillation is a very familiar topic with me. Actually, in standard model, the neutrino is predicted by the mass loss because the right-handed neutrino does not participate in the standard model interaction. It is a singular and the no electric charges. So they was the predicted by the no mass. Actually, it's the neutrino oscillations drops the between the blades different blades between the oscillates, and it argues that the neutrino is the massive particle. So there are so many solar neutrino sources like the solar neutrino. The first solar neutrino problems argue that the neutrino is the oscillation circles, and the atmospheric neutrino from the cosmic light, and also after writing neutrino, which is invented by the humans, so there's a neutrino beam, and also reactor neutrinos from the power plant. Also, the cosmic neutrinos they can be objects which comes from the astrophysical sources. Neutrino physics is a very good topics in this day, like as a Monroe neutrino or stellar neutrino anomaly, or like as a leptogenesis thing. So that was it. And the 2014, the WLED inventions that we see as optics. Also in 2013, the Higgs mechanism. The Higgs particles are discovered in the sun, LHC, Large Hadron Collider, in the 2012, and in the 2013, the Higgs and England received the Nobel Prize as the theoretical team to construct the Higgs mechanism. Actually, the idea of the Higgs mechanism comes from the condensed matter solid state physics to explain the spontaneous metal breaking in some superconductivity. So all the elementary particles should have the mass, but for the gauge symmetry, like as U1 gauge symmetry or SU2 chiral symmetry, the elementary particles should be the massless. But the Higgs, if the Higgs get the vacuum expectation values over its potential, then they can provide the particles mass by the Euclid interactions or gauge interactions through the scalar field. So that was the Higgs mechanism, and 2012, the individual quantum system, I don't know about very well. And 2011, the accelerating expansion of the universe, which is evidence of the dark energy. Almost the 1990s, they observed the supernovas type 1A, and the supernovas 1A can be the standard candidate because they have constant luminosity. And by using the relation between the luminosity and the intensity of the light, we can calculate the distance of the star from our Earth. And by plotting the losses together, we can plot the relation between the lattice and the distance. And by using the Hubble law, we can know that the expansion is of the universe. And if we detect the supernova type 1A, the universe expands acceleratingly. So that's evidence of dark energy. And actually, I read the article for the dark energy in some one science magazine, and that makes me to get the interest in the physics and the cosmology and the astrophysics. Actually, I read that article in the 2013 December when I was in middle school. And that kind of thing make me to get interested in the astronomy and the physics. And when I was high school in 2016, there was some contest of the Nobel Physics Prize, and I participated there. I wrote the essay and the presentations, make the presentations about the dark energy and the Nobel Physics Prize. And 2010, the 2D graphene experiments we see. 2009, the optical fibers for the communication that we see, but and the CCD sensor, also CCD sensors adapted to detect sort of observes in the telescope in camera. 2008, the spontaneous matter breaking. The spontaneous matter breaking means that the backup state is not invariant under the transformation. So there was a degenerate vacuum, and if we transforms, if we make the transformations, the accident, the vacuum state and the vacuum states are not invariant. So such a spontaneous matter breaking is deeply related with the Higgs mechanism. Also, there are several types of spontaneous matter breaking, like the electroweak phase transitions or chiral perturbation theory, from the curriculum plasma to the some of the meson states like variables about this type. And also in 2008, the CK matrix for the curriculum mixing is also receives the Nobel Physics Prize. That is the Kobayashi-Markakis matrix. So there are several generations of the quark, up, down, some signs, top, bottom, and they are mixed together, and it's called the CK matrix. And in the CK matrix, there are CP balancing phases, so that they make the CP balance. I think so. Many particle physics, Nobel Physics Prize are related to the Japanese. Also for the CK matrix, and for the linear there are PMNAS matrix for the laptop mixing. So there's a related exist on the Japanese physicists. And for the spontaneous matter breaking, as I was just, there are always the number of stone bosons appear with the same numbers of the broken symmetry. And the 2017, 2007, magnetic resistance, we see. 2006, CMB anisotropy. So the cosmic microwave backgrounds appears after the recombination, so the universal transference, so the light can go slice forward, and uh, the cosmic microwave background is the one evidence of the Big Bang theory, almost isotropic, and no spatial dependent, no time dependent microwave backgrounds with the 2007 three Kelvins, like the come to the Earth in the every angles and every time, and there's evidence of the Big Bang theory. And even though they are almost isotropic, but there are small anisotropy, which comes from the temperature and density perturbation, and is some of the precise measurements for the large-scale structures and the premature density perturbation. And many satellite makes a port to the Symbian isotropy. Actually, I should learn about the Symbian isotropy, but maybe that's a future plan. 2005, the optical coherence, quantum theory, and the Bragg sequence for the optical techniques. And 2004, asymptotic pattern of the strong interaction. That's also some important topic. That strong interactions for the QCD, that's is a non-abelian gauge theory. And for the such a non-abelian gauge theory, the beta function is a negative with some specific values of the number of the fermion and the generations. And the meaning of the negative beta functions mean that in the higher scale, the theory becomes the coupling becomes small if we calculate the learning coupling. So in the high energy, there will be the calculum plasma appear and the solar interactions coupling becomes extremely small. But in the low energy, there will be the color confinement. So by the color perturbation theory in the one under the electron volt, the bound size, like as the mesons and the baryon will appear as a curve mount. When conversely, the QD case with the Yuan gauge theory, they show the different behavior. The beta function is positive. So in the higher scale, they have the lambda of 4, but in the lower scale, they with IR3. So they received the Nobel Prize by the synthetic rhythm for the strong interaction. 2003, the superconductor around the superfluid, which is still fixed in the condensed physics. And 2002, the cosmic neutrino detections and the cosmic accelerators already mentioned, the neutrinos are the good topics. And the 2001, Bose-Einstein condensations, such as in the Bose-Einstein statistic, topic of statistical physics, and in the low energy, low temperature, the stated condensates to the ground state. And in the 2000s, semiconductors heterostructure and IC integrated circuits listed. And 1999, the normalization in the electroweak theory. So electroweak theories are actually the spontaneously symmetry broken, but even though that such a spontaneous symmetry broken theory, they can be renormalizable. And Atup and the Bartman's verifies that such a renormalizability of the spontaneous symmetry breaking theory. And 1998, the Brownian charges in the quantum fluid, condensed physics. 1997, logic link atom 12 is also important topics in atomic physics. 1996, the superfluidity is the helium-3. In 1995, the tau lepton discovery and the neutrino detections. The neutrino detection case, the Linus receives the Nobel Prize. He is the very big one. And the 1994 neutron spectroscopy and diffractions received. In 1993, Nitai Pasta, astrophysics, astronomy. And the 1992 particle detection with a multiple chamber. 1991, complex system with a liquid crystalline polymer. And the 1990s, the deep inelastic scattering, so-called the DIS. The scattering between the electrons and the photon, then we can prove the internal structures of the photon by using the DIS. And there are some several theory like the Super-Jorkin scaling or some of the relations, and that is evidence of the quark model. There will be the quark and the gluons in the photon, and by using the form factors and the structures functions, we can multiply there is the three quarks and the gluon, and the many C quarks in the proton. Okay. And 1989, the atomic clock and the ion drops technique. Atomic clock is also important subjects in atomic physics. 1988, muon neutrino discovery by using some beam experiments. 1987, superconductivity in the ceramic material. 1986, electron microscope and the scanning tunneling microscopes received. 1985, the quantum Hall effect receives also the topics with the abundance masses. And 1984, W-jet boson discovery. In the weak interactions, the W boson and jet bosons exchanges during the interactions, and they have the mass. So they even though the coupling is not too small, but the W-jet boson mass make the weak strength of the interactions, because the master of WG boson is instances in the propagator, so in the low end of the scheme, by using the four-parameter theory, the parameter constant becomes extremely small, and it makes the weak strength. 1983, the star evolutions, which is the research about Chandra Sekhar, and atom elements formations in the universe. And 1982, the critical phenomena in the phase transitions by the Wilson is also famous in the quantum field theory. He is originally the celestite physicist, but such phase transitions and renormalization groups formalism, so-called the Wilsonian RG, is famous in the quantum field theory. Okay, so 1981 lies the spectroscopy and electrospectroscopy. 1980s, CP violation in the K-mass system. So in the K0 and K0 bar system, there is a CP violation, which coming from the DKM quark mixing. And 1979, electroweak theory, which is the research is by the Sheldon Glacius, Abdus Salam, and Stephen Weinberg, so-called the GWS theory. The electroweak structures can be combined. So there's originally U1 hypercharged times SU2 Laplace symmetry, but they are broken by the Higgs mechanism, and the gate bosons mix each other, and as a result, only the electromagnetic U1 symmetries are remain, but the SU2 symmetry is broken, and it makes the massive W-jet boson. And also the hypercharge on the hypercharges and the weak charges are mixed. So the hypercharge and isospin, yeah, they are mixed each other. So that if we just weak charges with the parity violation, there's a VR structure, vectors and action vector, and the electric charges becomes the linear combinations of the hypercharge and the old isospin. That's the electroweak theory, and the coupling is sort of the electromagnetic interaction and the big interactions also given by the combinations of the original U1 times SU2, determined by the Weinberg angle. So that's the electroweak theory, a very elegant way to describe the natures by the standard model. 1978, the CMB discovery and the low temperature physics. Panjas and Wilson discovered the CMB by using the microwave and that becomes evidence of the idea of the layer emissions. 1977, electromagnetic disorder system. And then 1976, J psi particle discovery. J psi is a CC bar. There are one charm character and one charm anti-character, and there's one evidence of the port Kirk and the experimental particle physics. And 1975, particle motion in the nucleus. 1974, first discovery in the astronomy. 1973, tunneling in the semiconductor and superconductor, and just observing fact. 1972, BCS theory, Baldwin, Kittels, and Philip Raptor. And 1971, holography. 1970, magnetism, hydrodynamics in plasma, and antiferromagnetism, ferrimagnetism. And 1969, the Koch model by the Murray Gell-Mann. He predicts some elementary particle Kirk by researching some of the optical law of the baryon and the meson, like a hadron. There are SS3 approximate flavor symmetry between up, down, strange Kirk. That's called the Kirk model. And by using the tensor products of that UDS symmetry, like the 3 times 3 times 3 gives us the Kepler's and octave. There's the Kirk model. Such as 3 times 3 times 3 means that the baryon, and the 3 times 3 bar means that the meson. So Gell-Mann predicts the Kirk model, and he received Nobel Prize. So this is 6 p.m. So only the 30-minute remain. Okay, I will reply the live streaming.
Welcome for the announcement of this year's Nobel Prize. Has today decided to award the Nobel Prize in Physiology or Medicine jointly to
Has this morning decided to award the Nobel Prize in Physics to has decided to award the Nobel Prize in Chemistry in equal shares to
The Nobel Prize in Literature is awarded to
has decided to award the Nobel Peace Prize to
award Sveriges Riksbankspris in Economic Sciences in memory of Alfred Nobel to
So only the 30-minute remain. For the announcement of the 2012 Nobel Prize in Physics in 8 October 2012. So continuing the reviewing of the previous Nobel Physics Prize, I served in the 1968 hydrogen bomb summer nuclear reactions in star in the 1967. Hans Bartas received many elements can be composed in the nuclear reactions. And then 1966, atomic resonance of the Kamato. 1965, now the contemporary theory by Tomonaga showing us from Feynman. They discussed some QED, quantum electrodynamics, and makes a Feynman diagram, and some showing equations or distances. Actually, such a contemporary theory is to calculate the amplitude by using the time-dependent perturbations of the path integral. So the particles interactions can be detected. Interactions of amplitudes can be calculated by using this as a contemporary theory. And the rhythm reaction is also important one topic. The KFT with the loop level and the shifts through the several parameters. 64 amplifies with the measures topics of atomic physics. 63 nuclear theory, nuclear shell structures, like automatic number. 60 lambda theory for the phase transitions with the critical phenomena. Lambda is also very famous physics in C. 61, the Hofstadter receives Nobel Prize for nuclear structure. and also the resonant absorptions radiation. And the 1960, Bob Sample as a one met those in the experimental particle physics. And 59, antiproton discovery. So the one antimatter, suffix antimatter, and 58, the Cherenkev's effect in the radiations. And 57, the parity violations. Young, Jennings, and Li Zhengdao. So we see by the parity violations of the weak interactions, the cobalt 6 he experiments that there is a parity violation of the weak interactions. And it's related to VI structure, but after structures with interaction in lateral large analysis. And 56 transistor effect. And the 55 lamp shift atomics bind structures in atomic system, analytic ones of the left one. And the 54, the Born interpretation of the wave function in the quantum mechanics. So the now the it's a we collaborate in the quantum mechanics. So the coefficients or the wave function or amplitudes influence the each basis represents the probability amplitude. So if we scale sort of that coefficient, the wave function, then it can be interpreted as probability. That is the origin sort of the quantum mechanics. Very important. Right. And 54 coincidences of methods encounter, and 53 phase contrast in the optics. And the 52 nuclear magnetic lattice crystal measurement, 51 accelerate atomic particle, 1950 photography for the nuclear process. Now the half parts of the 20th century. And 1949, the nuclear interactions with the Hugo. So he researches the interactions between the meson, so-called nuclear potential, which is the decrease in distance with the exponential function. Such nuclear interactions also can be adopted in the interaction between the scalar particle and the spinor field. So actually, when he invented the nuclear interaction, he considered interaction between the meson particle or meson mediated, but actually nuclear interaction can generalize applied to the interaction between the Higgs and the barometer. He gives the dust barometer mass. So I want to
Welcome for the announcement of this.
so almost 1,077 people waiting for Nobel Physics Prize. Around 10 minutes remain. And 1948, Klaus Samba as the experimental method for particle physics. 47, atmospheric Platon layer as earth science. 46, high energy physics. 90, 45, Pauli, so receives the prize by the Pauli's executive principle. Very famous principle. Also, this is ending years of the World War II. 44, lab utilization for the two-level system in atomic physics. I will here handle physics. And 43, magnetic moments of the proton. And during the 1940 to 1942, there's another Nobel Peace Prize because Nobel does the World War II. And also okay, very good. Hi, and the 39 cyclotron, 38 neutron interaction, irradiation by the Fermi, 37 electron diffractions by the crystal lattice, 36 the cosmic radiation, and the positron anti-electron discovery by the Anderson, and the 35 neutron discovery by the Chadwick. Now the historical things, the neutrons are discovered, which compose the nucleons. Okay. Okay, many people are waiting now. This is the evening in the Korea. 6 p.m. I hope I can participate in the 7 p.m. slot. 33, Schrodinger equations of the wave mechanics and quantum mechanics, and the Dirac equation of relativistic mechanics. Very historical. 33, 32, matrix mechanics of the quantum mechanics by the Baron Heisenberg. Also historical. Raman effect. And the voice wave lines quantum mechanics thing. Wave particle duality. 923, Richardson effect. 27, Kempton's scattering is evidence of the photon. And the paths of the charge particles are errors. Hyperheat. 26, the discontinuous structure matter. 25, the theory for the electron in the atom. 24, XY spectroscopy. 23, elementary charge of electrons by the molecules, the oil experiments. 22 is the Bose atom model of the very historical. And 921, photoelectric effect as evidence of the photon by the other side. And 9220, anomalies in noise, Nickel steel alloy. And 99 stark effect, the electrons in the electric field. And 1918, analytic contact about Max Planck, the start of quantum mechanics. 17 is Röntgen radiation, characteristic Röntgen radiation. 15, the crystal structures by the Bragg, by using the diffractions and the lattice, and the low temperature liquid helium on us. He invents a very low temperature with the improvements of the varieties. And also there's a type of also materialized the gas accumulates in the Saddam. And 11th, is displacement low for the radiation. It becomes generalized in the Planck radiation formula. And 90 time van der Waals gas, very historical, the generalized stations reside gas. Yeah, many people like as on Mars and the multiverse here. Right. And 99 wireless telegraph, 98 is photography with interference. 97 Mike Carson interferometer. The stars of partial relative theory, evidence of the constant speed of the light. There's no materials light. And 96 electron discovery, very historical. Now the electrons are discovered. J. Thomson, already he discovered in the 19th century. Cattell's ray, argon gas as the non-activities. And the particle radiation and radioactive radiation by the QIst. And the Zeeman effects, splitting in the photon transitions in an atom. And the first Nobel Physics Prize in 19 One, abstract discovery, love analysis. So I review some work by Zoll and have a very good times to so almost I makes a 40-minute waiting and 10 minutes 15 minutes for me. So during the 15 minutes, I want to maybe those are side waitings. Hey, 10 minutes only.
Welcome for the announcement of this year's Nobel Prize. Has today decided to award the Nobel Prize in Physiology or Medicine jointly to
has this morning decided to award the Nobel Prize in Physics to has decided to award the Nobel Prize in Chemistry in equal shares to
The Nobel Prize in Literature is awarded to
has decided to award the Nobel Peace Prize to
award Sveriges Riksbankspris in Economic Sciences in memory of Alfred Nobel to
So 9 minutes left. And the Korean time 6:20 p.m. 24, 25, 26. So 2008, 48 people are waiting. Many people are waiting for them. Vietnam, Uganda, Netherlands, Iran, South Korea, Nepal, Denmark, Space, Republic of Taiwan, Science, Pakistan, Plato, Japan, Nepal, India, Brazil, India, Brazil, Australia, MIT, Mars, India, Italy, Turkey, Greece, India, Germany, and because of my predictions, quantum computing, India, astrophysics. Good morning from Brookfield. Very basics for the quantum physics, quantum computing. Big Bang theory, quantum computations are languages for the cosmic influential model sign up for the particle theory. Elon Musk and astrophysics. Also, Japan, quantum museum, quantum mechanics, quantum computing are reusable lookup. Quantum computing. Sheldon Cooper's Big Bang Theory drama. From the China, Europe, Germany, France, India, many people white, but from the South Korea. Now the 3,000 people already. I hope they wasn't. I don't know. So just a 6 minute. From is it from here on? Four thousands, almost 5,000. So Nobel Physics Prize. Any minute left. Right. Nobel Physics Prize. Starting from now the 10,000 people. Wow. All the physicists in the world wait for the Nobel Peace Prize from Singapore. 3, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 9, 8, 7, 9. So now the 1 minute, almost 20,000. people. 1 minute before preparations of the announcements, another 60 minutes remain. Now the time 16, 15, 14, 13, 12, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 60, 59, 57, 56, 55, 54, 50. Okay, now is the streaming will be waiting. 47, 46, 45, 44, 46, 42, 41, 40, 39, 38, 37, 35, 37, 31, 30, 30, 29, 24, 27. Now the 2000 people. Yeah, streaming start. Oh, down.
Welcome for the announcement of this year's Nobel Prize. Has today decided to award the
Very well. Oh, I think that's not the problem. Almost 1,000, 10,000 people. So the stream started in the 2 minutes ago. Streaming start. Starting time for all the places in the world. 30 minutes. Left. 8,000 people. Streaming starts.
We are on time.
2 minutes ago.
So the Secretary General and the experts from the committee will arrive within 15 minutes or so. And I think you have all, you know how to use the microphone. Please push the button, see that you get the green light both down here and at the top. And then you can talk. And after you have asked your questions, please press the red button to turn it off. And I think all of you have also seen the frequencies that we use at the Royal Swedish Academy of Sciences. And please do not use any of those frequencies because we need them. Thank you.
Please the content. Reassess of decoding. And that is there are no analytics and cosmology. Oops, high physics, but not sure. Because there are no or not. The column is well done. Now 10 minutes left. Nobel Prize. Welcome to the milestone of the 2024 World Physics Prize in Physics. We are streaming live streamed from the Royal Saudis Academy, so it's the Science Curriculum, Sweden Titanium. Okay. For sure. Now 10 minutes.
Sorry. It's going to be tight, I think. Är du okej med det? Att han slår nöjd?
One hundred 17 times is 91. Number of the Nobel Prize after 91. There's 124 individual. Good morning, good afternoon, good evening. Oh, many projects come company. Hey, minute left. Now we are all in the historical moment. 7 minutes left. Welcome to the announcement of 2024 Nobel Prize in Physics. We are streaming live from the Royal Swedish Academy of Sciences of Sweden. Lab hours in the 11:44 CRC. The physics prize awarded by the Royal Swedish Academy of Sciences of Sweden. The physics prize has been awarded in the 170 times it was 91. 125, so 4 individuals have been awarded the physics prize. And that's the person to be awarded the physics prize that was the last president at the age of 25, Prague, for the diffractions. The oldest person to be awarded the physics prize was also asking the age of 96. Now the 6th minute. Five minute. 우리 안 들어서건. The historical moment. One thousand people. So almost 1 hour waiting. Now 5 minutes. 5 minutes left. Oh, a low speed. I think I should stop the chatting. Now 4 minutes. Finish house in the 11 minutes ago. 4 minutes. Another physical parts now smells into the zone, solid glow, optical eyes. Minutes. 180 seconds. I buy my chatting. Cosmology Johannes physics. So I have the 7 p.m. on appointment. I hope I can participate. Nobel Physics Prize. Historical moment we all share together. And after that, I will go outside from the lab. Minutes 30 seconds. Minutes 17, 16. One minute. We are all together in this historical moment. Exactly 1 minute left. 59:58. Wow. We are waiting. Announcements for the Nobel Peace Prize. Jason Tonipo. 30 minutes left. Wow. And if I can. Wow. 16, 14, 13, help. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, live. Start. Oh, they don't start now. Now they get in. The room. Announcement. Preparation for the name card. Yeah. They get in the room. Preparation. They sat down, chair, and start the announcement.
Välkommen till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i fysik. Welcome to this press conference and the Royal Swedish Academy of Sciences, where we will present this year's Nobel Prize in Physics. We will keep to our tradition and begin the presentation in Swedish and then continue in English. And you're of course welcome to ask questions in either language later on. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. Till höger om mig sitter professor Ellen Måns, ordförande i Nobelkommittén för fysik. Och till vänster sitter professor Anders Irbäck, ledamot av Nobelkommittén för fysik och expert inom ämnesområdet. My name is Hans Ellegren. I'm the Secretary General of the Royal Swedish Academy of Sciences. And to my right is Professor Ellen Måns, Chair of the Nobel Committee for Physics. And to my left is Professor Anders Irbäck, member of the Nobel Committee in Physics and expert in this field. Årets pris handlar om maskiner som lär sig. This year's prize is about machines that learn. Kungliga Vetenskapsakademin har idag beslutat att utdela 2024 års Nobelpris i fysik till John Hopfield, Princeton University, USA, och Jeffrey Hinton, University of Toronto, Kanada, för grundläggande upptäckter och uppfinningar som möjliggör maskininlärning och artificiella neuronnätverk. The Royal Swedish Academy of Sciences has today decided to award the 2024 Nobel Prize in Physics to John Hopfield, Princeton University, USA, and Jeffrey Hinton, University of Toronto, Canada, for foundational discoveries and inventions that enable machine learning with artificial neural networks. Professor Ellen Måns will now give us a short summary of the prize. Please.
Thank you. Learning is a fascinating ability of the human brain. We can recognize images and speech and associate them with memories and past experiences. Billions of neurons wired together give us unique cognitive abilities. Artificial neural networks are inspired by this network of neurons in our brains. This year's laureates for the Nobel Prize in Physics, John Hopfield and Geoffrey Hinton, used fundamental concepts from statistical physics to design artificial neural networks that function as associative memories and find patterns in large data sets. These artificial neural networks have been used to advance research across physics topics as diverse as particle physics, material science, and astrophysics.
Statistical physics, particle
They have
physics,
also become part
they
of
are
our
applied.
daily lives,
They are related to
for
the
instance in
statistical, yeah.
facial recognition and language translation. The laureates' discoveries and inventions form the building blocks of machine learning that can aid humans in making faster and more reliable decisions, for instance, when diagnosing medical conditions.
Nobel Prize.
However,
Machine
while
learning.
machine learning has enormous benefits,
John
its
Hopfield
rapid
and,
development
Hinton.
has also raised concerns about our future. Collectively, humans carry the responsibility for using this new technology in a safe and ethical way for the greatest benefit of humankind.
Thank you. Professor Ebeck, are you ready to give a more detailed presentation?
Thank you.
Please.
Now I can make a presentation.
Yeah. So this year's Nobel Prize in Physics is about artificial neural networks. Today, we know that this is a powerful computational approach. This was not evident 50 years ago, but it was known that we mammals are very good at pattern recognition by some sort of computation in our brains. And this sparked an interest in understanding the collective properties of networks of simplified neurons connected by couplings with a strength that could become weaker or it could become stronger. And the idea would then be to determine the strengths of the couplings to achieve a certain function, and doing that by training the network on many examples. A breakthrough came in 1982 when John Hopfield presented a dynamical network which could store and retrieve memories and associative memories. The memory had simple binary 0-1 nodes, all nodes connected, pairwise connected. The states that remained unchanged with time were identified as memories. Moreover, it was possible to introduce an energy similar to energies one has in studying magnetic systems in physics. And that energy had the property that it was low in the states corresponding to memories.